You know, what's the one thing we have that the dinosaurs didn't? A space program. Today, we're going to talk about planetary defense. And this isn't some sci-fi movie plot. This is the real-world science of how we stop the next Earth-shattering asteroid from ruining our day. It's one of the most incredible, ambitious projects humanity has ever taken on. So, let's just think about this for a second. 66 million years ago, a rock the size of a mountain slammed into our planet. I mean, the impact was like 10 billion atomic bombs going off at once. The dinosaurs, well, after dominating the planet for more than 160 million years, they had a really, really bad day. They never saw it coming, and they had absolutely no way to stop it. But here's the thing. We do. And that one fact, it changes everything. We are literally the first species in the history of this planet that can look up, see a threat coming, and actually, do something about it. So, how do we do it? Okay, so when you think about stopping a giant asteroid, where does your mind go first? Yeah, I thought so. It probably goes right to the movies, right? The big, loud, dramatic, explosive solution. I mean, it's the obvious question, isn't it? If a giant rock is headed our way, why don't we just nuke it? We've got thousands of them. Let's just blow the thing to smithereens. Well, the reality, according to the actual research, is that's a really, really bad idea. Potentially catastrophic, in fact. You see, Hollywood sells us this idea of a clean vaporization. One big boom, problem solved. But the scientific reality is way messier. It's called the shotgun problem. See, a lot of these asteroids aren't one solid chunk of rock. They're more like loose collections of gravel and boulders, just kind of held together by their own weak gravity. So if you hit that with a nuke, it's not like breaking a rock. It's like shooting a beanbag with a shotgun. You don't solve the problem. You just turn one big threat into hundreds of smaller radioactive threats, all still hurtling right at us. So, if we absolutely had to use a nuke, scientists have a much smarter plan. They wouldn't try to blow it up. Instead, they'd use this really clever technique called a standoff detonation. You don't hit the asteroid, you detonate the nuke a few kilometers away from it. A massive wave of X-rays then instantly vaporizes a thin layer of the asteroid's surface, and all that vaporized rock blasting away, it creates a rocket effect. It literally pushes the asteroid gently but firmly onto a new, safer course. It's all about a precise nudge, not a chaotic smash. But even with this brilliant plan, you've got the human problem. First, there are legal hurdles. The 1967 Outer Space Treaty pretty much forbids weapons of mass destruction in orbit. But even bigger than that, can you imagine the political fallout? Let's say one country launches a rocket with a nuke on it and says, "Don't worry, it's for an asteroid." How can any other country be 100% sure that's true? Yeah, exactly. So for all these reasons, the nuke is the absolute last-ditch, break glass in case of emergency option. Okay, so thankfully, we're not just relying on the nuclear option. Scientists have this whole toolkit of other ideas that are way more predictable and a lot less politically explosive. And the best part? These are the tools they are actually building and testing as we speak. 14,000 miles per hour. That's how fast NASA's DART spacecraft was traveling when it smashed into its target. This mission was the very first real-world test of an idea called the kinetic impactor, which is basically a fancy way of saying hit it with a spaceship. And the idea behind DART was just beautifully simple. Just ram a refrigerator-sized spacecraft into an asteroid and see if you can nudge it. And in 2022, that's exactly what NASA did. The result? It was a wild success. It changed the asteroid's orbit by 32 minutes, which was way more than anyone expected. But here's the mind-blowing part. The studies showed that the biggest push didn't even come from the spacecraft hitting it. It came from the recoil. All the rock and dust that got blasted out into space from the impact, that ejecta gave the asteroid a second, even more powerful shove. How cool is that? So DART delivered the punch. But to really understand what happened, well, the crime scene needed an investigator. We had to go back and actually survey the damage. And here's why this is so important. Remember what we said about rubble piles? Most asteroids aren't solid rocks. They're more like floating bags of gravel. Just a bunch of boulders and dust held together by their own weak gravity. And hitting that is a completely different ballgame than hitting a solid object. Figuring out that difference is absolutely crucial. And that brings us to the next chapter in this story. The European Space Agency's Hera mission. It's literally on its way there right now to be that forensic investigator. It's going to map the crater dart left, study what the asteroid is made of, and, this is the really cool part, it's going to use radar to look inside the asteroid. That's how we'll get the real data we need to understand how these rubble piles react. But not every solution has to be a cosmic punch. If we spot a threat decades in advance, we can use something much more elegant, called a gravity tractor. The idea is simple. You just park a heavy spacecraft next to the asteroid and fly alongside it. That's it. The spacecraft's own tiny gravitational pull acts like an invisible tow rope, and over many, many years, that gentle, constant tug is enough to slowly but surely pull the asteroid onto a completely different, much safer path. Okay, so we've got all these amazing tools, right? Kinetic impactors, gravity tractors, even the standoff nuke. But they are all completely useless if we don't see the threat coming in the first place. And that really brings us to the most foundational challenge of all. You can't stop what you can't see. So take a look at this. This is where we stand right now. We've actually done a fantastic job finding the really big, extinction-level, dinosaur killer type asteroids. We found over 95% of them. But when it comes to the smaller, city killer ones, asteroids big enough to wipe out an entire city, we've only found about 40%. Let that sink in. 60% of them are still out there flying around, and we have no idea where they are. And a big part of the problem is that a lot of these asteroids are like charcoal black. Trying to spot one against the blackness of space with a normal telescope is like trying to find a black cat in a coal cellar. But that's all about to change. NASA has a new telescope coming online, the NEO Surveyor. And it's a game changer because it hunts in the infrared. It's not looking for reflected light, it's looking for heat. And because asteroids are warmed up by the sun to an infrared telescope, they glow like light bulbs against the freezing backdrop of space. It's like switching on night vision goggles. So when you put all of this together, the new ways to find them and the new ways to move them, it really points to a massive shift in how we think about our place in the solar system. Think about it like this. For our entire existence, we've basically been living in a cosmic shooting gallery, just hoping we don't get hit. Now we're becoming active managers of our celestial neighborhood. We're learning the traffic patterns, and we're building the tools to keep our little corner of the universe safe. And this is so important. This isn't just one country doing this. You've got global groups like the International Asteroid Warning Network that are coordinating observatories and space agencies all over the planet. They're even running real-world drills. In fact, a recent near miss was actually used as a live test, and it proved that the global communication and tracking systems really work. What we're building here, when you get right down to it, is a planetary insurance policy. And that, right there, is the ultimate takeaway. For 4 billion years, life on Earth has just been at the mercy of whatever the cosmos decided to throw at it. But now, for the very first time, something is different. There's this great quote from the research that just perfectly sums it all up. For the first time in the 4 billion year history of life on Earth, the target is starting to push back.